This is ASFurther Maths. We are in Unit 2 matrices. We're getting towards the end and we're looking now at invariant points. So an invariant point is one which is unchanged under a transformation. The origin O is always an invariant point for linear transformations represented by matrices. Invariant line is one which is unchanged by a transformation. So for example, if we have the line y equals 2x, I'm picking that at random, and we plot it, and we take any point. So what are the coordinates going to look like in that? It's going to be t and 2t, and we put it through a certain matrix. It'll come out and plot any point on it, and then it just lands again right on this line. And it says points do not necessarily map onto themselves, but onto another point in the same line. We only consider invariant lines that pass through the origin. So the first one says, what are the invariant points under the transformation in the reflection y equals x? So the reflection y equals x, again, if you look back or work it out, it gives you this matrix here. And what does it do? If you reflect y and x, it changes the x coordinate to the y coordinate, and the y coordinate to the x coordinate. If you multiply this out, it's a weird example, but 0, 1, and yx. So the x coordinates go to the y coordinates, and the y coordinates then go to the x coordinates. So i.e. any point on the line y equals x. What about example 2? The invariant lines in the reflection y equals x. 0, 1, 1, 0. So a line, if it's going through the origin, is going to be of the form t and mt. And whenever we multiply it out, it should give us t dash and m t dash. So that's a different point then on the same line. So let's multiply this out. We get mt t equals t mt. So what do we have? We have mt equals t dash, and we have t equals m t dash. So we could sub it in and get a few values out. So we know where t is our mt dash. So I'm going to exchange this t here for an mt dash. So it's m upon m t dash is t dash. That means m squared t dash is t dash, and if we divide through by t dash, we get m squared is 1, and that means m is plus or minus 1. So I found the gradient of any lines, so i.e. the two invariant lines are y equals x or y equals minus x. Sorry, that should be minus x. Does that make sense? I think it does. So it's a reflection of the line y equals x, so any point here just goes straight onto itself. Any point here, reflect this point here, it lands on the line, reflect this point here, it lands on the line, and so on. And so that example then works out. Let's look at our next example. What are the invariant points under the transformation by the matrix M 5, 3, 3, minus 3? Points and lines, sorry. So invariant points, first of all. 5, 3, 3, minus 3. And we want to know the points x, y that go straight down to x, y. So that means 5x plus 3y equals x. And it also means 3x minus 3y equals y. You could do this a couple of different ways. The x on its own, so if we rearrange this, we're going to get 3y equals minus 4x. And rearrange that, that means x is minus 3/4 y. I can now substitute this in here. So we have 3 at column minus 3/4 y minus 3y equals y. Now there's no other way, there's y's in each of these, just no other ways it's going to have. Terrible example really, minus 9 over 4 y minus 3y equals y. And we get a crazy amount of y, so minus 5 1/4 y is y, and y is 0. So the only points that are invariant under this line are y equals 0 and then x equals 0. So the invariant points are these ones here. Invariant lines. So what way do we want to set this up? 5, 3, 3, minus 3. They always have to go through the origin. So if we pick a point t, then the y coordinate must be mt, and we're trying to find their values of m. It goes to another point on the same line, so we represent that as t dash m. T dash, multiplying out again, 5t plus 3 mt is t dash, 3t minus 3 mt equals m. T dash. We're going to try and find our values of m, so how are we going to do that? We're going to substitute in, so we know t dash equals this, so I'm going to change my t dash here for a 5t plus 3mt. So I'm going to substitute that in. That's going to give me 3t minus 3mt equals m upon 5t plus 3mt. That gives me 3t minus 3mt equals 5mt plus 3m squared t. There's a t in every term, so it's going to cancel. And then I'm going to take everything then over to this side, so I'm going to get 3m squared plus 8m minus 3 equals 0. That factorizes. We'll not run through that now, but 3m minus 1 upon m plus 3 equals 0. That means m is a third and m is minus 3. So the two lines that are invariant under this matrix here are y equals a third x and y equals minus 3x.